Hello, and welcome to the WindowsSCOPE Rootkit series tutorial on ShadowWalker. ShadowWalker is a proof-of-concept rootkit based on the fact that Intel IA32 CPUs have two translation look-aside buffers, better known as TLBs, one for data and one for instructions. As you may know, when you access a memory address in a Windows program, you are really accessing a virtual memory address located in a page of virtual memory. This address must then be linked to a frame of physical memory through the process of address translation. You can learn more about this in our videos on virtual memory management. As mentioned, IA32 systems support a dual TLB architecture. These TLBs act as a cache for the CPU and provide a means of rapid lookup of recent address translations. The data TLB stores the addresses of data pertaining to a running process, and the instruction TLB contains the addresses of code segments that will operate on that data. The TLBs are primarily hardware controlled, but there are several software mechanisms for manipulating them. Although the two TLBs are normally synchronized, ShadowWalker implements an exploit to desynchronize them for potentially malicious purposes. The rootkit is able to insert incorrect address mappings for data entries and a desired rootkit driver. This allows ShadowWalker to present false information to non-rootkit drivers. ShadowWalker is composed of two kernel drivers, mmhook.sys, which does the split TLB trick, and a slightly modified msdirectx.sys driver that holds the core of the FU rootkit. This demo will be performed on an isolated system that I put together to specifically analyze ShadowWalker. This tutorial will have two main goals. First, I will show you how to use the WindowsSCOPE tool to detect the presence of rootkits on your computer. This will include an analysis of a few key signs that malicious software may be present on your computer, followed by detection of ShadowWalker on a live system. Once we have detected ShadowWalker, I will show you how to use the helpful features of WindowsSCOPE in order to analyze its functionality. This will include an in-depth analysis of the two drivers, msdirectx.sys and mmhook.sys. Let's get started by looking at some of the ways in which WindowsSCOPE can aid you in the detection of malicious software. For example, in this snapshot I have loaded both of the drivers, mmhook and msdirectx, which together form the rootkit ShadowWalker. In order to find any suspicious activity, we will direct our attention to the interrupt descriptor table. Windows does not regularly modify the contents of this table. Therefore, unless you have installed a new version of Windows, or a major update such as a service pack, you should not expect any changes. WindowsSCOPE allows you to easily compare the contents of all the operating system structures. I will compare the contents of the current snapshot, which is denoted by the asterisk, with the other snapshot labeled clean. By regularly taking snapshots of your computer with WindowsSCOPE, you can easily detect any changes made, with or without your consent. In this case, you can observe that entry number 14 has been modified. As you can see, the target module is now mmhook.sys instead of ntoskernel.exe, the native operating system kernel for Windows. This type of change is quite suspicious. Therefore, we would immediately investigate further into mmhook. mmhook is located under the drivers list, and once you select it, you can immediately see another red flag. mmhook was not present in any other snapshot before. You know this because there is no comparison available for this driver. Drivers are only installed when you make a hardware change or install new software. If you haven't done this, you can conclude that this driver may be malicious. You can investigate how mmhook is intending to handle the interrupt that it placed on the IDT by going into its code, but we will look into this functionality later. By comparing the important operating system structures, drivers list, or the process table, you can easily find malicious code, since these are common targets. Another way of finding malicious code is by looking into the Open Files node under the Summary of System Activity. There are a large number of files open, and therefore we will use the Compare feature again. This highlights new open files in green, and as you can see here, there are only a few which are new to this snapshot. This technique is most effective if the snapshot is taken soon after boot up, since the open files right after a system boot don't change very often. Here, you can easily see that ShadowWalker is a new file running with executable writes directly from your desktop. As you may know, most programs install under the Program Files folder, so this file would also raise a red flag. This would prompt us again to look into the particular file. At this point, we now know what signs to look for as indicators of malicious software and how to use WindowsSCOPE to detect those signs. After performing these checks, I have determined that ShadowWalker is in fact present on my machine. The next step will be to use the tool to analyze the functionality of this rootkit. Our analysis will include looking at the two rootkit drivers, msdirectx.sys and mmhook.sys. We will begin with msdirectx. This driver is a modified version of the FU rootkit and has two main responsibilities. First, it must be able to remove the incorrect address mappings put in the data TLB by ShadowWalker. This will guarantee that only the rootkit can get access to its true data. Second, it must locate and unchain a malicious running process from the process list. This makes the process invisible to the operating system and in turn the user. Let's start by looking at a snapshot with only msdirectx loaded and see how it is able to access the correct rootkit data. We are going to analyze the code under the graph view in order to understand its functionality. Here, you can see one of the first things done is storing the address F87F4004 in the register EDI. Then, CL, a register which is normally used to store interrupt values, is loaded with the hex value 2. Once this is finished, the address stored in the register EDI is called. This address points to KF raise IRQ level, which when called, raises the IRQ level to 2, according to the argument loaded into CL. Any device configured to use IRQ2 will actually be using IRQ9, corresponding to an open interrupt level. This will allow the driver to perform instructions without being interrupted, meaning that no other running programs can access the true data being used by this driver. Before attempting to access any of its global data, msdirectx must first flush the TLB entry corresponding to that data to clear any incorrect mappings established by ShadowWalker's mmhook.sys driver. For example, here, the invlpg command is used to flush this specific data TLB entry in order to remove the address mapping stored in that page. The driver then establishes the correct mappings and performs whatever data manipulations it requires. The TLB must then be flushed again to remove those correct mappings. Now, if a program were to request this data, a page fault would occur, and ShadowWalker would generate fake mappings corresponding to fake data. We will look at that functionality shortly. Once the flush is completed, the IRQ is lowered back to its previous level using KF lower IRQ level. This completes a single data access. Now, we will look at the functionality msdirectx uses to hide a running process. The first step is to get the name and location of the process this driver will be hiding. Once this has been established, a new kernel-level system thread will be opened by the driver. The sole purpose of this system thread is to continually check the process list and hide any process with a desired string in its name. By opening the function represented by this node on the graph, we will further investigate how msdirectx hides a running process. While the system thread created by msdirectx is active, this function will be continually called. As an argument, it takes a prefix which marks any function that will be hidden. The first task is to check if the supplied prefix is a null pointer, and if so, jump to a return. The function then saves the name of the last process in the process list and begins to iterate through this list. Each process is checked against the hide prefix using the string compare function. If a match is detected, this function is called. It removes any process containing the hide prefix from the circular linked list of processes by making the neighboring processes point to each other rather than to the hide process. Processes not containing the hide prefix remain unchanged. This continues until all processes in the list have been visited. WindowsSCOPE will allow us to see exactly what the hide prefix is through navigation to the strings view for msdirectx.sys. Here, we can see that the string FU is present in the data section for this driver. Therefore, any processes containing this prefix will be removed from the process list and hidden from other processes. This concludes our analysis of msdirectx.sys. We will now turn our attention to mmhook.sys. This is the ShadowWalker driver used for hiding the existence of msdirectx by diverting access attempts to the rootkit data. In order to understand this process, we will look at how mmhook verifies that Shadow Walker is compatible with the system it is running on, how it detects and hides the rootkit driver, the installation of the IDT hook for the page fault interrupt, and the functionality of the Shadow Walker page fault handler. We will perform this analysis by looking at a snapshot with both MS-DirectX and mmhook loaded. Notice that with mmhook loaded, MS-DirectX.sys is no longer visible on the drivers list. It is important to note that the law enforcement and enterprise versions of WindowsSCOPE will have additional methods for scanning processes and drivers. This in turn would allow us to expose the hidden driver. Let's start off by looking at the initial code that is run for mmhook. This is the setup code that is used to verify that Shadow Walker is compatible with the system it's run on, as well as to locate the driver Shadow Walker will be hiding. The pages of this driver are then added to the hooked page list used by the fake page fault handler. Shadow Walker can only function properly on single processor systems without hyperthreading. Therefore, this function will call the KE query active processors function and keep track of the number of processors reported. This value is maintained in the ESI register. Here we can see the register is compared with the number 1. If the number of active processors is not equal to 1, the flow proceeds down this path, calling functions to report the error. Shadow Walker will then exit without setting up the memory hook, and thus not hide the driver. However, if it is determined that the system has only a single processor, the control flow will proceed down this path. This block corresponds to the setup of function arguments for hiding the driver. Here, we see that the value 7 is pushed onto the stack. This tells Shadow Walker to hide all aspects of the driver, including data, code, and header from other processes. Here, a pointer to the name of the driver to be hidden, MS-DirectX in this case, is also pushed onto the stack. This name can be seen by looking at the strings for mmhook.sys, just as we did previously for the hide prefix of MS-DirectX. Finally, the function for hiding the requested driver is performed. Let's navigate to the function address in this call and see how Shadow Walker will hide MS-DirectX. I have a link to this function saved in my workpad. Let's open that now. The first step in hiding the driver will be to locate it in memory. Here, the function will use the input module name, MS-DirectX, as an argument to call this function. The execution of this function will yield the base address of the input module in memory. If that is successful, this function will be called to find the number of pages in the range of that module. Once the boundaries of the module have been discovered, all that is left to do is to hide the desired sections of the module. The driver sections will be hidden through the use of this function. It will take each of the input pages within the input driver section and mark them as invalid. Now, access attempts to these pages will be forwarded to the Shadow Walker page fault handler, which will present fake data on read or write attempts by any non-rootkit driver. Also, the pages of the driver sections to be hidden are added to a list of hooked pages. This list acts as a hash table, allowing quick access to hooked pages to minimize Shadow Walker's impact on system performance. Page faults generated by any address that is not in this list will be passed down to the original system page fault handler. In the case of MS-DirectX, all sections will be hidden, making the driver completely invisible to other programs. At this point, we have now seen how mmhook determines Shadow Walker's system compatibility, locates the rootkit driver to hide, and how it ensures that page faults will be generated each time there is an access request to the driver. We will now look at how the Shadow Walker page fault handler is installed through the use of an IDT hook, and conclude by looking at the functionality of the Shadow Walker page fault handler. Let's first examine the function which mmhook uses to hook the IDT, placing its own code at entry number 14. I also have this function stored in my workpad, so we'll load it now. IDT entry 14 is used to point to the page fault handling routine. The first thing that the hook function does is disable interrupts so that no page faults can be processed while the hook is being inserted. This function then fetches the base address of the IDT using the SIDT instruction seen here. Next, this function is called to fetch the address of the page table entry for the IDT location to be hooked, and write protection is removed so that the entry can be changed to point to the Shadow Walker page fault handler. Once the entry is writable, the address of the old page fault handler must be saved before the hook can be installed. Here, we see the top and bottom halves of the old handler address are stored in EAX and ECX respectively, combined together into one complete address, and stored on the stack for later use. Next, the address of the new page fault handler is fetched from the stack and stored into the EAX register. This register is then broken into two halves. These halves are combined and written to the IDT to overwrite the target address for the page fault interrupt handling routine, completing the IDT hook. Page faults will now be directed to the new page fault handler. Finally, IDT write protection is restored and interrupts are re-enabled. We can use WindowsSCOPE to verify that the IDT hook has been installed by viewing the target address and target module of IDT entry number 14. Here you can see how the tool exposes the hook. This entry has been modified and is pointing to an address that is not in ntoskernel.exe or hal.dll, which contain most of the interrupt handling routines. Now that we have seen how the IDT hook is installed, and use WindowsSCOPE to verify that it has in fact been installed, all that remains is to analyze the functionality of the ShadowWalker page fault handler. By going to mmhook.sys at this particular address, we can see the code which will be executed for a page fault interrupt. We will search for the hook's target address and graph it on the workpad. Let's look at the entry node, and we can see that one of the first things being performed is to check whether the processor is in user mode. The register EDX in this case contains the current mode of the processor. If the processor is in user mode, then the page fault is passed down to the original handler by this jump, as you can see by the arrow. If the processor was not in user mode, then the next check to be performed is to see if the faulting address is a user mode address. When a page fault occurs, the faulting virtual address is stored in the register CR2. We will compare this register against the highest user address, and if it is in fact a user address, it will be passed down to the original page fault handler because ShadowWalker does not hook user pages. If this is not a user address, then the next check is performed. This check is to make sure that the page is part of the hooked list. This would mean that it belongs to the driver which ShadowWalker is trying to hide, in this case msdirectx.sys. This node performs that check, and once it is done, we will know if the faulting address corresponds to a hooked driver page. Once we get to this point, we know the page needs to be hidden. This portion of the code does some comparisons in order to determine if the page which we are trying to hide is a large page or not. If it's not a large page, we're going to perform some modifications. If it is, we go directly to the code which determines if the page fault was due to an execute or a read-write request. Here, you can see the program counter is compared against the register which contains the faulting address. If the two are equal, then it means that this is an execute, and a procedure similar to the regular page fault is followed. Data access requests originating from the Rootkit code are handled in a similar manner. If this is not the case, then we know it's a read-write from a non-Rootkit driver, and we need to take a different approach. In this code, a fake page table entry is being loaded into the register ECX. In this next line, EDI is loaded with a real page table entry for the faulting page table address. Next, the header for the real page table entry is extracted, as well as the page frame number for the fake one, and the two are concatenated together into the ECX register. The real page table entry is saved in EDX. Next, interrupts are disabled, and the patched page table entry is put in place of the real one. This next instruction sets the valid bit for the loaded page table entry, and a fake data access is performed. Once this is done, the valid bit is set back to 0 so that the page is marked as not present. Finally, the real page table entry is restored and interrupts are re-enabled. This completes one iteration of the ShadowWalker page fault handler. This process will be repeated each time the operating system produces a page fault interrupt. This concludes our analysis of the ShadowWalker rootkit. After watching this video, you should have a more thorough understanding of how you can use WindowsSCOPE to perform detection of malicious software. Also, we were able to detect the presence of ShadowWalker on our demo system, and finally analyze the rootkit's functionality by using many of the tool's helpful features. Thank you for watching, and please view our other tutorials.